Question 1. 3 bags A, B and C each contain 1 red marble and some green marbles. Bag A contains 1 red and 9 green. Bag B, 1 red, 4 green. And bag C, 1 red, 2 green. Sasha selects at random 1 marble from bag A. If he selects a red, he stops. If it's green, he continues and takes one from B. If he selects red, again he stops. And if it's green, he continues and selects one from C. So part A, draw a tree diagram to represent this information. So part A, we're going to draw a tree diagram. So for our first pick, we can have red or green. So we can pick red or green. If it's red, we're going to stop, so there's going to be nothing more. If it's green, we're going to pick from the second bag, which again can be red or green. So the second bag can be red or green. And if it's red, we stop. If it's green, we pick again from the third bag, bag C. And again, that can be red or it can be green. So we've got bag A, bag B, and bag C. Let's write in the probabilities. So for the first bag, 1 red and 9 green. So 1 out of 10 are red and 9 out of 10 are green. For the second bag, bag B, 1 red, 4 green. So 1 out of 5 red, 4 out of 5 are green. And bag C, 1 red, 2 green. So 1 out of 3 red and 2 out of 3 green. So that's our tree diagram. Find the probability that Sasha selects 3 green marbles. So we're going to multiply across the branches. So it's 9/10 times 4/5 times 2/3. And I'm just going to use the calculator. So 9/10 times 4/5 times 2/3. And that's 12 out of 25. Part C, find the probability that Sasha selects at least 1 marble of each colour. So, well, we can do green. We can't pick red first. We can have green red or green green red. They're the only 2 options. So we may as well just work them out. So green red or green green red. So green red is 9/10 times 1/5. And green green red, I'm going to put a plus. So I'm going to add up these 2 probabilities, add up the probability of green red and the probability of green green red. So green green red is 9/10 times 4/5 times 1/3. So that's green then red or green then green then red. They're the only ways we can get 1 of each. And again, I'm just going to type this into the calculator. So 9/10 times 1/5 plus 9/10 times 4/5 times 1/3. And that's 21/50. part D, given that Sasha selects a red, find the probability that it's from bag B. So we want the given formula. So the probability that it's a red from bag B, given we've got a red. So we want the probability of a red from bag B divided by, you divide by what's given, and that is that a red is picked. So a red is picked. So a red from bag B, given that a red is picked. So the probability we get a red from B is 9/10 times a fifth. That's our red from a B option. And well, the probability of getting a red at all. So let's do that first. So red from B is 9/10 times 1/5. So probability of a red from B is 9/10 times a fifth, and well, that's 9/50. The probability of red is picked at all is going to be 1 minus the probability of getting 3 greens. So we could work it out. We could say it's going to be 1/10 plus 9/10 times a fifth plus 9/10 times 4/5 times a third. But that's every other option than what we worked out here, the probability of 3 greens. So it's 1 minus 12/25, which is, well, 13/25. So we have probability of red from B, 9/50, divided by 13/25. And I will type it in the calculator. So divided by 13/25. So that's 9/26. And that's it. Question 2. So we've got a partially completed box plot showing the distribution of daily mean air temperatures using data from the large data set for Beijing in 2015. An outlier is defined as a value more than 1.5 times the interquartile range below Q1 or more than 1.5 times the interquartile range above Q3. The lowest 3 air temperatures are 7.6, 8.1 and 9.1 degrees Celsius, and the highest is 32.5. So complete the box plot showing clearly any outliers. So we need to calculate the outliers. So we need the interquartile range. So the interquartile range we can work out from the box plot we've been given. So we've got 26.6 as our upper quartile. So 26.6 minus the lower quartile, which is 19.4. So our interquartile range is the upper quartile, take away the lower quartile. So 26.6 take away 19.4 is 7.2. So that's 7.2. So we want 1.5 times the interquartile range, 1.5 times the interquartile range above the upper quartile, which is going to be 1.5 times 7.2 above 26.6. So So 1.5 times 7.2 above 26.6 would be 37.4. So 32.5 is not an outlier. Or we want the lower quartile, which was 19.4, take away. So the 19.4 take away 1.5 times the interquartile range, which was 7.2. So 19.4 take away 1.5 times 7.2 gets us to 8.6. So anything below 8.6 is an outlier. So 7.6 and 8.1 are both outliers. So on a box plot, what are we going to do with our outliers? We're going to mark them with a cross. So 7.6 and 8.1. 7.6 and 8.1. We're going to mark with crosses. And then for the bottom whisker, we can use 9.1. We can also use 8.6, but let's use 9.1. So 9.1 is here. Our highest value was 32.5. And we'll join them up. So there's our box plot. Using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. So this is Beijing in 2015 from the large data set. So we need to know where the lowest temperatures are, where these temperatures have come from. And the large data set's May to October. So October, because it's the coldest, suggests from which month the two outliers are likely to come. October, the coldest month. And using the data from the large data set, Simon produced the following summary statistics for the daily mean air temperature for Beijing in 2015. So we've got N, 184, the sum of X, 4,153.6, and SXX, 4,952.906. So show to three significant figures the standard deviation. So the standard deviation, this is in the formula book, this formula. The standard deviation is the square root of SXX over N. So all square rooted SXX over N. So we want the square root of this 4,952.906 over N, which was 184. So the square root 4952.906 over 184, 5.19 to 3 significant figures, and that's what we wanted. Simon decides to model the air temperatures with the random variable. So T is distributed normally with a mean of 22.6 and a variance of 5.19 squared, so a standard deviation of 5.19. Using Simon's model, calculate the 10th to 90th into percentile range. So we've got a normal distribution, and we know the mean and the standard deviation. So let's just make a note of them over here. The mean is 22.6, and the standard deviation is 5.19. So we want the 10th to 90th percentile. So let's get our calculator. We'll go into the menu, and we've got our distributions here, number 7. And what do we want to work out? We want inverse normal, number 3. So the area for the first one, we want 0.1. And we've got the standard deviation of 5.19, the mean of 22.6. So the 10th percentile is 15.948747. I will write it all down for now. So store as A. I just 15.9. So 10th percentile, 15.9, and I've stored it as A. And we'll go back in. We want the area of 0.9 now, 90%. Again, standard deviation, 5.19. Mean 22.6. So I'm going to click through here, and I've got 29.3. So the 90th percentile, 29.3. So our 29.3 take away our 15.9. So that's B take away A. So menu number 1 again. And alpha B take away alpha A is 13.3. So these were rounded, weren't they? 13.3 to 3 significant figures. And again, it's in degrees. Simon wants to model another variable from the large data set for Beijing using a normal distribution. State 2 variables from the large data set that are not suitable to be modeled by a normal distribution. Give a reason for each answer. So what from the large data set can we not measure using a normal distribution? Well, the wind speed from the Beaufort scale conversion, Beaufort conversion, is not numerical data. So we can't model that. with the normal distribution, and of the other ones, which one is not, or which ones are not normally distributed. And rainfall is the obvious one because there are lots of zeros, so it's not normally distributed. So rainfall has lots of zeros, therefore it is not a normal distribution. Question 3. Barbara is investigating the relationship between the average income, GDP per capita, X US dollars, and average annual carbon dioxide emissions, Y tons, for different countries. She takes a random sample of 24 countries and finds the product moment correlation coefficient between CO2 emissions and income to be 0.446. Stating your hypothesis clearly, test at the 5% level of significance whether or not the product moment correlation coefficient for all countries is greater than 0. So our hypotheses, so H0, the null hypothesis, is going to be that the relationship, so it's for the population, so I'm going to use a P, is 0. So our null hypothesis is that the PMCC, the product moment correlation coefficient, is 0. There's no correlation. Our alternative hypothesis is going to be that it is positive. It is greater than 0. There is a positive correlation. So we've got 24 countries, and we're going to look up the critical values. So let's use the table. So in the formula book, we've got critical values for correlation coefficients. It's quite a long way back in the book. It's on page 35. And N is 24. So N is 24. We've got a 5% significance level. So 24 at 5%. So this is our critical value. This 0.3438. So that's the critical value. N is 24. 5% significance level. 0.3438. So the critical value at a 5% significance level is 0.3438. And we've got 0.446. So it's above the critical value. So it's in the critical region. So 0.446 is bigger than 0.3438. So it's in the critical region. We can reject H0, reject the null hypothesis, and accept H1. And that means there is a positive correlation between, what was it, income and CO2 emissions. Average income income and CO2 emissions. Okay, part B. So Barbara believes that a non-linear model would be a better fit to the data. She codes the data using the coding. So M is log 10x, C is log 10y, and obtains the model C equals negative 1.82 plus 0.89 m. The product moment correlation coefficient between C and M is found to be 0.882. Explain how this value supports Barbara's belief. Well, 0.882 is closer to 1 than 0.446. It's a stronger positive relationship. So we can say 0.882 is closer to 1. Therefore, it's a stronger positive relationship. And part C. Show that the relationship between x and y can be written in the form y equals ax to the power of n, where a and n are constants to be found. So let's change it to x and y. So we've got c equals negative 1.82. C equals negative 1.82 plus 0.89 m. And C is log 10y. And M, was it log 10x? Is log 10x. And we need to make this y equals. So let's get the logs on the same side and everything else on the other side. And we'll probably be better off with 1.82 being positive. So I'm going to plus 1.82 to both sides and take log 10y away from both sides. Now this is 0.89. If I'm going to divide these, or change the takeaway to a division, I want to get it up, jump it up, so it's the power of x. So I've just got log 10s left. So I'm going to have log 10x to the power of 0.89 minus log 10y. When we've got a division, when we've got a subtraction between two logs, we can change it to a division. So we've got 1.82 equals log 10, and we've got x to the power of 0.89 over y. And now we can get rid of the log. So 10's the base, 1.82 is the power, so 10 to the power of 1.82 is equal to x to the power of 0.89 over y. We want y to be the subject of this, so we'll multiply both sides by y and divide both sides by 10 to the power of 1.82, which will leave us with y equals x to the power of 0.89 over 10 to the power of 1.82. Now that's almost in the form we wanted. We wanted y equals axn, so we just need to find, well, what a is really. So we need to change this 1 over 10 to the power of 1.82 times x to the power of 0.89. So let's change this into a number. 1 over 10 to the power of 1.82. So we've got 0.0151. Did it say 3 significant figures? It didn't. We'll just go with it. So we'll say y equals, we'll give it to 3 significant figures. So 0.0151 x to the power of 0.89. Question 4. Magali is studying the mean total cloud cover in octas for Lucas in 1987 using data from the large data set. The daily mean total cloud cover for all 184 days is summarized in the table below. One of the 184 days is selected at random. Find the probability it has a daily mean total cloud cover of 6 or greater. So 6 or greater, that's these 3. So we have 52 plus 52 plus 28. Out of the total, which is 184. So let's just type this in the calculator. And we've got 33 over 46. So that's the probability that we get 6 or more. Magali is investigating whether the daily mean total cloud cover can be modeled using a binomial distribution. She uses the random variable x and believes that x is distributed binomially with n of 8 and the chance of success as 0.76. Using Magali's model, find the probability that x is greater than or equal to 6. So the probability that it's greater or equal to 6 is going to be 1 minus the probability that x is less than or equal to 5. So if we work out everything up to 5 and do 1 minus that, that'd be everything 6 or above. So let's use our calculator. So we've got a binomial cumulative distribution. So we are going for our distributions again. Binomial cumulative distribution. Variable. So we want up to 5 when n is 8. And our probability is 0.76. So we've got a probability of 5 or below as 0.297. So if we do 1 minus answer, so menu 1, 1 minus answer, we've got 0.703. And the second part to part B, find to 1 decimal place the expected number of days in a sample of 184 days with a total cloud cover of 7. So we want a 7 this time. So the probability x equals 7. So back to our distributions and binomial probability distribution, variable. So x is 7, n is 8, and the probability was 0.76. We've got 0.28. Did it say 2 decimal places? 1 decimal place. 0.3. Oh, sorry. Find the number of days in a sample of 184 days. So it's the probability times 184. So answer times 184, 51.7. So answer times 184 is 51.7. So what was the answer? Divide it by 184 again. 0.281. So 51.7 days. Explain whether or not your answers to part B support the use of the model. So we need to compare these two. So 33 over 46 is 0.717. So that's close, isn't it? From the model is close to the actual. And 51.7 days with 7, 52. So yes, they are both close. The answers support the model. (51.7) is close to 52, and 0.717 is close to 0.703. There were 28 days that had a daily mean total cloud cover of 8. For these 28 days, so these are the days with a cloud cover of 8, the daily mean cloud cover on the following day is shown on the table. Find the proportion of these days when the cloud cover is 6 or greater. So this is out of 28, so 5 plus 9 plus 9 over 28. So 5 plus 9 plus 9 over 28. (0.821). Comment on Magali's model in light of your answer to part D. So when the day previous had a cover of 8, the chance of getting more than 6 the next day was bigger. So this probability has gone up. So it's not, the cloud cover one day isn't independent of the cloud cover the day before, or it suggests it isn't independent. So the model may not be reliable because for a binomial distribution, we need everyone to be independent of the previous one. Be reliable. Our daily mean cloud cover the answer suggests daily mean cloud cover is not independent from one day to the next. Therefore, not a binomial distribution. Question 5. A machine puts liquid into bottles of perfume. The amount of liquid put into each bottle, d milliliters, follows a normal distribution with a mean 25 milliliters. Given that 15% of bottles contain less than 24.63 milliliters, find to 2 decimal places the value of K, such that the probability of D being between 24.63 and K is 0.45. So here we've been given the mean, but not the standard deviation. And we're going to need to work out the standard deviation. And to do that, we can use this information. Well, 15%, we can use the standard normal. So we can use Z equals X minus the mean divided by the standard deviation. And we can find this Z value using the 15%. We've got 2 ways of doing it. There's a table in the formula book, and 15% will be one of the ones given to us. Or on our calculator, if we go to our distributions, our inverse normal, and our standard normal distribution has got a standard deviation of 1 and a mean of 0. So we can leave these as they are and just type in the area of 15%, 0.15. So press equals, and there we have our Z value. So Z is negative 1.036432 and so on. So negative 1.036 equals our value that we're using, 24.63, minus the mean, 25, divided by the standard deviation. So we can work out the standard deviation, multiply both sides by the standard deviation, and divide both sides by negative 1.036. So we have, to go back to our normal calculator, menu 1, 24.63 minus 25 over what we just stored as A, which was our negative 1.036. So we've got our standard deviation of 0.35 0.357. And I'll store that as A now instead. So what was the question? The value of K such that we've got, I'm going to draw a diagram here. So we've got a normal distribution. We've got the mean of 25. Down here we've got our 24.63. And we want 45% up to K. So this is 15%. Another 45% will get us to 60%. So K's up here. So we've got 35% here and 10% here. So in total, we have 60%. So we're 60% of the way through. So let's use that 60%. So we'll go to our calculator, back to our distribution, back to our inverse normal, an area now of 60%, and our standard deviation is 0.357. Our mean is 25, and we get 25.09. 25.09. So K is 25.09. A random sample of 200 bottles is taken. Using a normal approximation, find the probability that fewer than half of these bottles contain between 24.63 milliliters and K milliliters. So it's a normal approximation. So the probability of a success is 0.45. So that's P. So P is 0.45, which means the probability of a failure, 1 minus P, is 0.55, and N is 200. So we're going to say that Y is distributed normally with a mean of NP and a variance of NPQ. That's our normal approximation. So we have NP 200 times 0.45, 200 times 0.45, and our variance 200 times 0.45 times 0.55, and 200 times 0.45 is 90. So that's the mean. The mean is going to be 90. So that's how many we'd expect. How many out of 200, how many we would expect to be between those two numbers. And our variance is that times 0.55, which is 49.5. And that means the mean is 90, and the standard deviation, mean is 90. The standard deviation is the square root of the variance. And we want to know the probability of half. The probability is fewer than half contain between these values. So fewer than half, that's n is 200, so less than 100, but we need our continuity calculation. So we want to know less than, so 100, the lower bound, 99.5. So 100 goes from 99.5 to 100.5. So we want less than 99.5 because the binomial expansion is discrete and the normal distribution isn't. So we need this continuity calculation, which means 100 goes from 99.5 to 100.5. So this is what we need to know. So we want our normal distribution, normal cumulative distribution. So the lower is, well, 0, upper 99.5, and a standard deviation of the square root of 49.5. And the mean, oh, it was 90. So we've got a probability of 0.912. So the probability that x is less than 99.5 is 0.912. The machine is now adjusted, so the standard deviation of liquid put in the bottles is now 0.16. Okay, so it's decreased. Following these adjustments, Hannah believes the mean amount of liquid put in each bottle is now less than 25 milliliters. She takes a random sample of 20 bottles and finds the mean amount of liquid to be 24.94. Test Hannah's belief at the 5% level of significance. You should state your hypotheses clearly. Okay, so we've got a sample. What question are we on? Part C. So when we have a sample, the mean is, well, the mean, and the standard deviation is standard deviation over the square root of the sample size. So the mean, well, let's do our hypotheses first. So H0, our null hypothesis, is that the mean is 25. So H0 mean is equal to 25, and H1, so she believes it's now less than 25, so H1 is the mean is now less than 25. So we've got a mean of 25 and a standard deviation of 0.16 over square root 20. There are 20 bottles in the sample. So mean, standard deviation, and our x, that's 24.94. 24.94. So what's the probability of x being 24.94 or lower? So we want to know 24.94. What's the size of this area? Or we could work out, alternatively, we could work out what 5% is and compare the two numbers. So we could also work out 5% and compare it to 24.94. Either one of these methods would work. Let's go the inverse normal. So let's work out 5%. 0.05. Standard deviation 0.16 over square root 20. And the mean 25. So 24.941. So 24.941. So that's 24.941. So 24.94 is in the critical region. So 24.94 is less than 24.941. So it is in the critical region, not in the acceptable region. It's in the 5% of most unlikely. So it's in the 5%. It's not in the 95%. So we can reject the null hypothesis. And accept H1. So we can say there is evidence to suggest the mean, what was it? Amount of liquid in a bottle the mean amount of liquid is now less than 25 milliliters.